70% of our planet is covered by water, and the vast majority of it remains a freezing, pitch-black void. We evolved at the surface, where we associate light and familiar proportions with safety. To the human eye, a brightly lit coral reef represents standard for a healthy, functioning ecosystem. But evolution prioritizes efficiency over aesthetics. In the deep, bodies are optimized solely to meet the demands of darkness, cold, and crushing weight. Reaching these depths requires massive industrial shielding. The extreme pressure and vast distances make the abyss a more restrictive environment for human exploration than outer space. As the submersible sinks away from the light, it enters a realm where the requirements for life are defined by physics and chemistry rather than sun and air. To understand these creatures, we have to look past our surface-based instincts and evaluate their anatomy by the rigid constraints of the ocean floor. Seawater absorbs sunlight rapidly. Reds and yellows vanish first, eventually leaving only faint blue wavelengths before the water turns completely dark. Many species survive here by becoming transparent. By stripping away pigments and allowing light to pass through their tissues, they eliminate the visible edges and shadows that would otherwise reveal them to predators. When animals do produce their own light through bioluminescence, they use it with extreme precision. A brief flash might lure a meal or confuse an attacker, but constant illumination is too energy-intensive to sustain. This lack of light forces a harsh trade-off for sensory organs. A species either develops massive lenses to capture every stray photon, or abandons vision entirely to reallocate those metabolic resources elsewhere. In a world without ambient light, survival depends on your ability to remain invisible while choosing exactly when and how to reveal yourself. At several thousand meters deep, the weight of the water column exerts hundreds of times more pressure than the atmosphere at sea level. This force is sufficient to collapse steel pipes and crush air-filled lungs. Abyssal organisms survive by matching this force. They replace rigid bones and air cavities with water-rich, gelatinous tissues that equalize internal and external pressure, preventing them from being crushed. Many deep-sea animals only look melted because of tissue damage. When they are dragged to the surface, the rapid decrease in pressure causes their specialized water-dense cells to expand and rupture. In water that hovers near freezing, metabolic rates slow to a crawl. Movement becomes a series of deliberate, low-energy hovers, allowing animals to survive for months on a single meal. These soft, slow-moving bodies occupy a narrow envelope of success, specialized to function under thousands of atmospheres of weight. Food is the rarest resource in the deep. Because nutrient density is so low, starvation is the default state, with predators often waiting years between successful hunts. This scarcity drives extreme anatomical traits, like unhinging jaws and elastic stomachs. These features allow a predator to trap and consume anything it encounters, even prey significantly larger than its own body. Reproduction presents the same challenge. In some species, if a male manages to find a female in the void, he fuses his circulatory system to hers permanently, ensuring genetic continuity in an environment where they may never meet another of their kind. When the chance of an encounter is nearly zero, evolution favors these irreversible, specialized behaviors over any requirement for aesthetic proportion. At the bottom, tectonic plates fracture, allowing superheated minerals to erupt into freezing water. Bacteria here generate organic matter by processing the toxic chemicals found in these plumes. This process, chemosynthesis, allows an entire ecosystem to function using Earth's internal heat instead of sunlight. These vents support complex life forms, like giant tube worms. Lacking eyes and digestive systems, they survive by housing colonies of bacteria directly within their tissues. These chemical oases operate in total isolation. They provide a model for how life might exist in subsurface oceans of distant moons, far beyond Earth. These organisms represent the outer limits of what life can become when pushed beyond the sun. What we once interpreted as a nightmare is actually a success story of survival in the most unforgiving realm on Earth.